Hello, everyone. Welcome to DevStandup episode 16. Today, our guest speaker is John Boero. John has 20 years of experience consulting around the world on information security, infrastructure performance, DevOps, and solution architecture. And today, he's a traveling nomad providing contract services and supporting the open source projects Fedora and Llama.cpp. Today, we are going to talk about the bottlenecks. The topics include maximizing the performance and monitoring with a focus on AI workloads. And we're going to cover the high level from the experiences such as storage bottlenecks and I/O nightmares, network overhead and packetization, terminal warnings and OM law, AI quantizations, hidden penalty, and memory bandwidth versus training and interference. It's like a really in-depth topic, so I hope we will get clear picture after the session. And I would like to pass the microphone to John, and he could start the presentation. So, John, here you are.
Perfect. Perfect. Thank you very much. Thanks for having me. Apologies, it's tough to align on time when I'm in Malaysia right now for a couple of more months. But I was honored to be approached by you and speak on some of my experience. So some of my background, as you mentioned, I've been consulting around the world for customers and for partners, likes of Red Hat, Puppet, and HashiCorp, as well as a couple of SIs and solutions integrators along the way. So I'll start with a bit of basics. This is the reason I've kind of done this topic. A friend of mine in the Bay Area was working on one of the AI startups, right? Where everybody's building their own training clusters, their own networks, and when they have performance issues, they don't necessarily know what to do, right? This is the younger generation that is working in the cloud, and they don't know how to monitor actual system performance and hardware. So I'll take you back through a little bit about how I started out probably about 15 years ago in the consulting scene when really hard drives were still the major bottleneck, right? Storage and I/O used to be a nightmare before solid state storage, right? So a lot of customers that I saw, a lot of enterprise customers, put a lot of money into big, expensive storage solutions that didn't necessarily perform. Right? You talk about a database that needs to read about 5 bytes of data before it can decide where it needs to read the next 5 bytes of storage. That took a lot of timing, right? You need to time the hard drive spinning, the reader heads accessing, as well as RPMs, calculate RPMs and how fast those drives are spinning. And in one case, I saw one particular customer, a public sector in the U.S., that had spent multi-million-dollar investment on a SAN solution from one of the big SAN providers, one of the big storage providers, using RAID 5. If you're familiar with the RAID solutions, this is a striped plus parity option. And the sales rep for this vendor had told them this would be faster than any local storage that they had, right? So they were told to essentially offload all I/O, including virtual memory, onto the single storage, right? The single SAN. And this is across hundreds of VMs, hundreds or up to 1,000 VMs, right? So in the case of Linux, those that are familiar with Linux, the concept of A time, right? Access time. Anytime you read a file, if access time is enabled, or what we have relay time, essentially when you read a file, it's going to create a write operation, right? It's going to essentially have to update a timestamp on the last time a file was written to, right? And that sounds all well and good on a solid state storage, but if you are talking RAID 5, a stripe needs to be read, right? A stripe needs to be read from the entire set of disks, whether it's 128K or 512 bytes or 512 kilobytes. It needs to be read from all those disks, and then a write operation needs to recalculate the parity from all of those stripes and write it back to disk. So essentially, 10 read operations result in 10 write operations, and each of those write operations is going to take an eternity in storage, right? This entire cluster, this entire state within a data center came crumbling down, right? It could not even perform faster than your local PC because the I/O was just extremely overloaded. In addition, they had set swappiness to 100. And if anybody knows about swappiness, that's how often or the likelihood that essentially prioritizes virtual memory being written to disk. So they were essentially told that their storage would act faster than their local memory, which is insane, right? They were using all of that storage as extended memory from their system. So everything that was being read and written to memory was attempting to be written to disk, right? I/O schedulers, and this is another concept that has kind of gone away with solid state. When do I read indirect storage, right? If your application says read this bit of disk, traditionally that is passed to the kernel and the I/O scheduler. And a lot of people have lost the ability to select the best I/O scheduler. And a lot of times that would accumulate reads and writes and say, okay, well, these writes are all adjacent on disk. I'm going to accumulate them until I feel like it, and then I select the optimum time to write that out to disk. That tends to be a bottleneck. Again, when you have a secondary storage system like the SAN has its own I/O scheduler, its own redundant sort of scheduling, and also the solid state disks will have their own solid state schedulers as well, right? So the need for a CFQ, which used to be the default in enterprise Linux, is largely gone, right? You don't necessarily need any kind of elevator or scheduler anymore with today's storage. Let the hardware figure it out for you, right? And again, I have a saying that's a little bit dark. Don't believe everything your storage sales rep says, and this includes cloud storage, S3, right? I remember the early days of OpenStack when customers were promised that OpenStack's object storage would be so powerful that they wouldn't need to use any local storage for databases, right? We had Oracle databases running on essentially S3, on essentially Gloucester storage, right? Fuse-based clustered storage, and also Ceph. And that's just not what it's good for. It's not going to perform that well. I also have seen the concept of Fuse file systems being misused. Fuse, if you're not familiar with it, is a file system in user space. I use them a lot. It's actually really good for making tools and quick access for small bits of data like REST APIs, presenting them as a file system. Do not use them for block storage, right? Kernel mode switches essentially are slowing you down. Linus Torvalds famously said these file systems are a toy, right? They are there. They can be used as a toy, but they're not going to be a high-performance file system. So don't use them for critical block storage. And in the case of S3 Fuse, like you can mount a local S3 storage volume, sorry, not a local, a cloud-based S3 storage volume as a local mounted file system. Well, that's real handy. But guess what? HTTP is overhead, right? So you're going to have the REST API be overhead, and you'll also have the Fuse context mode switches, user mode switches, be a bottleneck, right? I could expand on that because I'm a big Fuse advocate when it's used correctly, but I'll just get straight to it. Storage bottlenecks, again, recommendations. I say choose your file systems wisely. Use the proper connectivity. NVIDIA bought Mellanox. That was one of their biggest acquisitions before they kind of have exploded on the AI scene. Mellanox was a specialist in InfiniBand, right? If you're not familiar with the difference between TCP, Ethernet, like Wi-Fi as well, and InfiniBand is a much more efficient protocol for data centers, right? TCP can send a packet across the planet, and Ethernet can send a packet across the planet with mixed fiber and copper and Wi-Fi and microwave, and it's going to have that control flow for lost packets. InfiniBand is a much leaner protocol, and it's going to get you the maximum bandwidth across the data center where you weren't necessarily going to lose a packet, right? Fiber channel was a hugely expensive option similar to this that people used in the data center for years. I don't care what anybody tells you, fiber channel over Ethernet or any solution like this over Ethernet and TCP won't perform the same as fiber channel and InfiniBand. Right? This is why NVIDIA acquired Mellanox, because they knew that this was required for their high-performance AI networks. Tuned profiles, if you're familiar with it, it's actually TuneD. TuneD is a service that is included in most enterprise Linux, Amazon Linux, Oracle Linux, Red Hat Enterprise Linux, obviously. These essentially automated a large part of my job, and they're super handy, right? Whereas I used to maybe do a week engagement around somewhere around the US or somewhere around the world to do custom tuning for a high performance database or high performance IO. This has largely been automated today, right? I use these all the time. They're great. The number of profiles available have skyrocketed. I used to show up in the early days of cloud to a customer that was running VMs, and the VMs were still trying to tune fan speeds and temperature sensors, right? There's no temperature sensors in a VM, and there's no fan controllers. So there is a tune profile or tune V profile for VMs, and it should be used when applicable, right? That will also, by the way, adjust your IO scheduling. Okay? Use solid state storage everywhere, right? It's affordable now. It's come down in price for archiving and long-term storage. Obviously, you have cloud storage options, right? But when you're using storage and IO, IOPS count, latency counts, you need to use solid state. Okay. Network again. I did a blog post on essentially UDS, Unix domain sockets, versus TCP in service meshes, right? And I talk about Istio, and you talk about communication between pods and between Kubernetes containers. Look at this. IP and TCP are massive overhead, right, for a local connection. And again, these friends of mine that were working in the Bay Area at startups, they were trying to communicate and cluster these AI servers using TCP, right, using Ethernet. Again, the reason NVIDIA bought Mellanox was to have this, right? Don't try to cobble together a network for AI and a high frequency, like an HFT, high frequency trading cluster over traditional networks, right? Traditional networks like TCP and Ethernet, again, are great for going around the planet. They're not the best solution for the data center. Right? And this is why those systems cost so much, right? Because they're worth it. Don't do storage over TCP, and don't do, again, AI training clusters over TCP. Use InfiniBand. Okay. If you do have to use TCP, again, larger clusters or maybe WAN, use jumbo frames where possible. This is a lost art as well. People don't understand that the TCP overhead on a packet is not something to ignore, right? The concept of MTU, the maximum packet size, traditionally being 1,500 bytes. Think about that. Each 1,500 byte TCP frame has to have that form filled out, actually, back here, right? Has to have all these details filled out. And this is great, again, for going around the planet, but, or I should say Wi-Fi, where connections and packets can be dropped. But think about this. There was the lost concept of a TCP offload, right? Servers about 10 years ago, 15 years ago, maybe, created this network concept called TCP offload. So put in the network card a dedicated handler for TCP packets. This was really great at the time when CPUs were not top of the line. They weren't quite as efficient as they are today. Somewhere along the line, CPU community, Intel and such, convinced everybody that the CPU was better at handling these packets, right? So they all in the industry declared that TCP offload was obsolete. Well, guess what? That was good for 10 megabit, 100 megabit, gigabit networks, but now we're talking about 800 gigabit a second Ethernet, right? The number of packets, jumbo frames or not, that need to be processed by the CPU has become overwhelming, right? So we're seeing the return of the TCP offload concept in the form of SmartNICs. And I think it's a great concept. I'm loving that I'm seeing this come back, right? Your CPU has better things to do than process TCP packets. It shouldn't be doing that in today's age, right? So this is something that we're seeing kind of help to bridge the performance gap between InfiniBand and Ethernet by offloading that back onto the SmartNIC. It's not going to be as high performant as InfiniBand, right? But this is something that should be paid attention to, especially in the data center when Ethernet and particular things like load balancers are going to need to minimize that latency, minimize that CPU overhead with those packets, right? So if you're in the networking space, and again, Some of my favorite problems to solve in the field were low latency networks, huge clusters, load balancing, and the ultimate dark arts, high frequency trading, right? If milliseconds count, nanoseconds count, and you get that trade in before your competition, it doesn't matter if it's nanoseconds or not, that is an edge that you have in the financial market, right? So things like this are going to make a difference. Jumbo frames, I remember the first time I saw a cluster again in a different government customer in the US where we enabled jumbo frames. It made a huge difference between the servers in a cluster, right? Again, if you're dealing with 10, 100 gigabit networks, the number of frames will dramatically increase if that TCP is being handled offloaded and those frames are the maximum size. This is something that really makes a difference in performance and also needs to be supported by all nodes on the subnet, right? So if you're a network engineer, I apologize, I probably just butchered your profession. I'm not a network specialist, but I have seen these things in the field, and I think that definitely the smart NIC return is something to look at. Again, that blog post on service mesh, if anybody's used Istio, or I come from the HashiCorp side console, Istio and essentially the Envoy proxy, software proxy that those services use to kind of redirect packets in between nodes. I should say in between pods, in between containers, nodes, and pods. Those can optionally use Unix domain sockets, right? So this is, in my mind, the software equivalent of InfiniBand. Along the development cycle, everybody thought they needed an IP. So Kubernetes essentially gave everybody an IP via containers, right? And then also meshed those together, right? So we have service discovery, we have routing through the kernel, actually through the software firewalls and essentially maybe overlay networks like Flannel or Calico. Those all overcomplicate the solution of communicating between pods and resources in the system, right? So I put a benchmark and I said, okay, if you use Unix domain sockets in your container, in your Istio deployment, or in your console service mesh, you essentially pass off your data, your socket, without packets, right? Unix domain sockets are direct. They're in memory, and they have no packetization. So you essentially have a raw feed of data in memory, which is multitudes faster, as you can see in this benchmark. It's a little misleading, maybe, but latency is red, right? So if I have a 4 kilobit transfer. Sorry, this is actually 4,000 packets, I believe. You can see the latency drop in Unix domain sockets because, again, this gap is that TCP packet overhead that you don't need to worry about, right? And the latency will be the same no matter what size you're using of a transfer. In this case, throughput, look at throughput. So TCP has about 1/5 the transfer speed as a UDS, right? Now, if I'm on a Kubernetes, if I'm developing on a Kubernetes cluster and I'm exchanging data between two pods, and those pods are on the same node, this overhead is completely wasted, right? I'm packetizing my communication. I'm sending it off to Istio, which is doing the essentially the encryption, the AES, right? That is then being forwarded to another pod, depacketized by that on the other end in software, and that's an amount of overhead that's going to drive. It's wasted, right? Your system shouldn't be handling all that overhead. If you use UDS, your service mesh is intelligent enough to figure out, okay, well, I can handle the user load, user application data in its raw form. If I realize that I need to packetize that, send that off to another node, I can do that. I have that overhead only when I need to transfer that across the network. So I've seen dramatic improvements on performance within a single node in a Kubernetes cluster just by switching to UDS. It's a little easy. It's a little bit of a strange kind of a concept to wrap your mind around if you've been using IPs your whole life. But it's actually very simple once you get through that. Okay. So I'm going to jump over to thermal bottlenecks. Any questions yet? We'll save them for the end. Okay. This is my favorite performance topic in today's 2025. Right. Again, my friends in the Bay Area, they have solid state storage. That's not the bottleneck. They have pretty tight knit networking. there's a little bit of overhead where TCP is used, but the real bottlenecks come in the form of thermal overhead, right? Again, cloud developers don't necessarily think about the temperatures of their systems. Essentially, VM developers, again, I've probably visited a dozen VMware customers that say, I have two identical VMs. They both say they're performing 100% on this workload, and one of them is doing 3 times the work. Why is that? And most of the time, I say, well, what's the temperature of your host? What's the temperature of your CPUs? What's the temperature of your RAM? And they have no clue because VMs don't report this. Go into the server room, go into the racks if you can. Use a thermal camera. I guarantee you that one of those systems is either not being cooled properly, has a broken fan, or a fan that is out, or is downstream from the cooler, right? It's actually cooling itself with already warmed air, right? Now, this makes a huge difference, right? So if I look at any performance benchmarks today, and I'll show some examples in a bit, if I look at Grafana, maybe some performance data from a CPU on a server, or an entire set of CPUs and cores on a server, they will say 100%, right? If you're running a full workload on all cores at once, whether those cores are running full speed or they're running at turbo speed, turbo boost, which is an Intel concept, or they're throttled to a quarter of their performance because they're too hot, it will register 100%, right? And that's misleading. So you do not want to see performance data without thermal data. This is something that cloud providers usually won't show you unless you're using a bare metal instance, right? So first of all, cross-match your, and if actually I look at here, I always, on my own systems, this is a laptop obviously, but I always have a dashboard that shows, in this case, cores, temperatures, and fan speed as well. I don't have fan speed up on this one currently, but always be able to show these in the same time series, right? And they can see my own network going with this video that I'm submitting, right? Now, if I do a workload or if I run a demo while I'm actually doing this video share, right, we'll see the core usage go up. We'll probably see the temperature go up as well. And this shows nothing about my actual core speed. And in addition, half these are hyperthreads, right? This is a hyperthreaded box. It's actually only got 4 cores. So there's only really 4 CPUs there. It's misleading because they're each reading different speeds and different performance, even though 4 of those are threads. Now I have got a separate laptop next to me, and it's actually got E-cores, right? So it's got 12 cores, 22, I think, with hyperthreading. 4 of those cores are efficiency cores, right? They're only going to run at a gigahertz tops, something like that. And that's misleading because they will all be compared at the same performance metrics in a uniform dashboard, right? So it's very misleading. Again, on a VM, you need to also worry about stolen CPU time, right? This is something that a lot of cloud providers either hide from you or don't show in your VM. Guess what? You're actually sharing your host with another VM, right? You're sharing your host with other customers. And what looks to you like 100% CPU utilization on a VM may actually be 50% because that host is handling other VM tasks, right? This is common. This is all over the place, right? And the same thing applies in the cloud. You see 2 VMs that are identical. One is actually working twice as hard as the other one, even though they both show 100% full throttle, right? They're both being used 100%. And if you're using Kubernetes, right, Kubernetes will allocate kernel namespaces and actually C groups, right? So it will actually say, okay, this container is allowed 2 CPUs or a certain number of CPU cycles. If you use HashiCorp Nomad, it's nice that it will actually create quotas for essentially CPU shares. Guess what? Those are not guaranteed, right? Those are essentially maximums, right? So if you're actually sharing a host that's overloaded, you might not necessarily get those. In some cases, you can actually overcommit. So you can allocate two cores or 2,000 CPU shares. And when there's more available, it will actually surge. So you need to actually benchmark and check what you're using, right? And this is my favorite Intel snafu, Intel kind of issue over the last probably 12, 13 years. Anybody that has a system with Intel Quiet Systems technology, essentially earlier generations of Intel, I'm thinking Westmere, if you're following the Intel generations, Westmere and older, would expose the system fans and the CPU fans as a pulse width modulator, right? In fact, I can go into this Linux machine here and I can say sensors, right? And I actually see core temperatures, I can see fan RPMs, I can see all of the temperatures involved, and I can also adjust those fan speeds. I can actually set the TuneD profile to say, okay, I'm max throughput, crank up the fans to maximum. I don't care if it's under load or not, right? The Intel generation that uses quiet systems technology put that into something called management engine, Intel ME, right? That was kind of like a subconscious chip off of the CPU, so that if the CPU crashed or maybe a lockup in the OS, that subsystem management engine, which contains quiet systems technology, would be able to control your fans for you, right, to make sure your system doesn't overheat. Those paying attention, management engine was declared compromised, right? There was a vulnerability built into the silicon, into the hardware, and Intel's only solution to that was to disable it, right? So they have an entire generation, multiple years of Intel servers that had essentially a hardware bug, and now you cannot see the fan speeds and you cannot control the fan speeds in your system, right? So if you're using, I think mine actually does. I have an AI workstation back in the US that is, I think, Ivy Bridge, and guess what? That has QST, right? So it is actually impossible for me to view the CPU fan speeds unless I provide an external cooling solution. So this is something that Intel wasn't proud of, right? This was something that really hurt them. Among their other vulnerabilities, Spectre and all the Rowhammer vulnerabilities that were affected. This was a dark time for Intel. I love Intel, but they have a generation of problems right now. So again, hidden chassis fans. If your hypervisor doesn't show you fan speeds, and again, in the case of QST, a lot of servers out there, hopefully, I think most of them are considered deprecated right now, shouldn't be in production. Skylake, I believe, Skylake systems, I'm not sure, some of them are still in production, would use QST. Double check your host, double check your cloud selections. And also, again, if you have on-premise technology, if you're using the latest generations, that shouldn't be an issue. Okay. We've essentially gone back to, as far as I know, system managed fans, traditional managed fans. So think about Ohm's law if you're an electrical engineer. Ohm's law essentially stating that volts and amps are tied to temperature, right? So if I, for example, on this box, if I do a massively parallel job, or if I do inference, let's say I do CPU inference on this right now, and I run an instance of Llama.cpp, it would be silly because it would run slow, but I could try that and say, well, guess what? All the CPUs are going to be maximized. All the temperatures are going to spike and the CPU speeds are going to drop. So again, it looks like all my 8 threads are being maximized, but actually the CPU temperature is slowing down. And guess what? I'm not using less power, right? I'm still using full power energy because it takes more energy to push those pulses through the CPU, right, when it's hot. This is why overclockers use liquid nitrogen, right? So I did an experiment. I'll get to the AI side in a bit. But I did an experiment with a customer that was running Llama.cpp inference on a couple of older GPUs. And I told them, like, well, it's not running as fast as you think because you need more cooling, right? And they have a server room in essentially a room temperature environment with fans, right? They're not using liquid cooling as they should. And I showed an example. I said, okay, I'll take a model that you have. I'll run inference on it, an inference benchmark essentially, complete 20,000 tokens, which gives it enough time to ramp up the heat, right? And essentially, you're maximizing your, in this case, GPUs. This is a older generation NVIDIA Volta or NVIDIA H100. I used a V100. My rig actually is pretty old now. It uses Volta 100s. I set it in a room during winter in the US, did the inference benchmark, 20,000 tokens, and it took something like 9 minutes. I don't have the exact facts. I took the same box, I put it outside in February, and I think in the Midwest you're about to get another blizzard, another cold snap. I think it was minus 10 degrees Fahrenheit. What is that? Minus 15, 20 Celsius. And ran the same benchmark, and it completed in half the time, right? Using the same amount of energy because that cooling is outside, right? Your box is cold, your box is happy. And again, if you're in the cloud, you better know your temperatures, right? Because it's up to your cloud to maintain your cooling solution. If you don't have visibility into that, what's your temperature? I don't know. If I were a cloud provider, I would want to make sure that my customers' systems are properly cooled. But guess what? If I'm not showing you the data, I'm not guaranteeing anything. Okay. So slower at higher temps. Again, you're still using more energy. So this machine, I think, the one that I'm on currently, can speed step or essentially scale the CPU speeds using speed step from 400 megahertz to I think 3.2 gigahertz. Again, it's a standard laptop. I think this is an 11th or 12th generation Intel. And again, if I'm running it hot and it's running at 400, 800 megahertz, I might be using the exact same amount of energy that a properly cooled system would be at 3.2 gigahertz. Right. So gamers, no. If you want a performance tuner, talk to a gamer, right? Talk to a gamer, talk to an HFT engineer if you can, right? Because temperature matters. And again, if you're not familiar with Phoronix Test Suite, these are the best benchmarks, I think, in the industry. I've used these all over the world. I love setting up a fresh install, a fresh deployment from a customer, spend a lot of money on hardware and benchmarking and say, okay, this is where you are. If I come back in a year and you're going slower, something is wrong, right? There's a failed fan somewhere, something in the hardware is off, or actually the software update has been broken. This has slowed you down. So again, how does this actually look in practice with the enterprise? Users of Grafana know. This is actually, funny enough, this is a community contribution. This is not NVIDIA's official Prometheus exporter. So if you're familiar with Prometheus, it's a real simple way to just output data in a text format that can be archived in a time series database and then viewed usually in a visualizer with Grafana, right? NVIDIA's official enterprise solution for this is part of a DGC, which is their data center essentially components. And funny enough, again, I actually prefer the community version of this. I blogged about this because the NVIDIA official node exporter is designed for enterprise GPUs, right? It's designed for their server GPUs. They don't have fans, right? So they don't bother reporting fan speeds in their Prometheus data. The community one, this one is actually pretty standard right now. I think it's not maintained anymore because it doesn't need to be maintained. And it exports everything from fan speeds, temperatures of the memory, whatever is available in the GPU, right? This is actually standard NVIDIA data from the driver. And again, this is Linux systems, right? So it works on just about anything. Now, funny enough, one time I had one customer that actually wanted to add some metrics into a Prometheus exporter. And this is something so simple that today vibe coding can be used really simply to create a Prometheus exporter instantly. In fact, if you're using AMD GPUs or Intel GPUs for an inference workload, right? Intel actually had some original Phi drivers, some of their original essentially server coprocessors. If you're using any non-standard or any maybe like an ARM GPU, part of the new up and coming ARM GPUs, just saw that Qualcomm introduced some patches for AI features in their GPUs. It's real simple to create a Prometheus exporter today with vibe coding. Just in fact, I even experimented with the AI shell that I created a couple of years back to say, okay, create a Prometheus exporter for me, or just output the metrics for Prometheus, including GPU speed, GPU clock speeds, fans, memory temperatures, and more. And it just creates it for you. Right? Super straightforward. Visualize it in Grafana. Simple enough, right? The community is really well established for this. Again, the server one from NVIDIA, the DGCM version, or DGC, will actually output only server-side GPU metrics. So I'm actually a fan of the community one. Make sure that you compare not just your GPU temperatures, right, your CPU temperatures, memory temperatures. Your motherboard in a server is full of sensors, and it's for a reason, right? So make sure that those temperatures are both recorded and logged and shown on a chart, on a graph over time, right? Because if you see a sudden spike in temperature, that should be a warning, and you can set up alarms and alerts in Grafana for that. Okay? So dashboard must, I got ahead of myself again. No performance data without thermal data, right? Always, whenever you can, show that thermal data, because performance data is meaningless without thermal data to say that you're actually not running at maximum speed. Show the time series trends, right? Not the current values. So it's one thing to have a big TV up in your office with the kind of like a speedometer or showing where your speed is currently. It's another thing to show graphs over time. And if there's a sudden spike in system temperatures during a uniform training exercise, right? Fine-tuning a model may take days, maybe take hours, depending on the cluster size. If you see an irregularity in temperatures, make sure that those systems are checked, because there's either a failed fan, and if it's a QST system, right, a fan failure might not necessarily be getting any notifications, right? Make sure to check all your hardware, make sure those anomalies are both alerted and handled, right? Make sure that there's if you're familiar with PagerDuty or any of those solutions, that will actually notify you. Okay? Align all the time series data in one view, right? So if I look at this one again, I never drive a car without a speedometer. I never use a computer without a dashboard like this, right? And this is KDE on Fedora. All of these charts and all these actual performance meters are going at the same speed, right? So if I see a spike in time for CPU usage here, that will coincide with a spike in temperature here. If I see a spike in memory usage or disk I/O, or in this case, I'm missing the fan speed sensor panel right here, those should all vertically align or align some way that is easy to understand, because you want to be able to relate those issues. And if you're familiar with the query language for Grafana to create those alerts, it's really powerful and actually kind of painful if you're not familiar. That's another thing that's really easily vibe coded. It's a create me a Grafana alert for this condition. Vibe coding is really good. In fact, Claude, I still use Claude for that whenever possible. It just does the best job. Show host data. Again, if you're in a VM, you're trapped. You don't necessarily have visibility into your fan speeds, your temperatures, or your actual system performance data. Right? Use bare metal instance. Make sure that you can see those metrics. Make sure that you can actually see the fan speeds, the temperatures, and such, and export them. Okay. Enable performance Prometheus metrics where possible. Again, browse the Prometheus exporters, because odds are there's a lot more than just your standard system outputs. Again, I actually vibe coded, I tried to vibe code a QST fan sensor. If you do enable management engine, like my AI workstation, it's not on the public network. I'm not worried about it being compromised. There is a way that you can monitor fan speeds with QST. In fact, I vibe coded one up, said, okay, I know this isn't supposed to be supported anymore. Enable management engine. Now use the system calls. This calls to go and get that data out of QST. It's not officially supported, but it is possible. Okay. Again, always alerts. Alerts for fan and cooling failures. These friends of mine in the Bay Area literally have GPUs melting. If you've heard of the NVIDIA GPU melting problem, there was a funny user on Reddit that actually flashed a custom firmware on an older gaming GPU from NVIDIA, and literally you could melt it. You could crank it up to 200 degrees, something like that, if you wanted to, and just melt it. All of those cooling alarms should be active. You should know when temperatures spike, not to the level where it's hazardous, but when they spike out of norm. And again, ECC errors. A lot of people trying to do AI on a gaming GPU. Guess what? There's a reason that those workstation and server GPUs cost more. So the former Quadro line in NVIDIA and the Fire GL Pro, or whatever the AMD workstation line is, those have ECC memory, preferably HBM, and I'll get to the actual memory bandwidth next. Make sure the errors are checked, right? If you're training a model for days and days, and suddenly a DIMM fails in one of your GPUs, or suddenly a memory cell fails, that can interrupt your entire process, right? And that's happened multiple times that I've heard of secondhand. That's a big operation. That costs a lot of money, right? Because there's a lot of energy poured in, a lot of bills poured in data center time and colo time or data center time that has to be restarted. So make sure that those GPUs are monitored, liquid cooled if possible. Again, you're supposed to get a cold snap in the Midwest US right now. It's a good time for AI. It's a good time for cooling your systems. So thermal suggestions: use bare metal instances for monitoring in the cloud if you're in the cloud. Use liquid or immersion cooling if you're on-prem. I've not seen a current version of NVIDIA's systems being immersion cooled. If you're familiar with that, they call it the deep fryer. It's essentially the entire server submerged in oil. There's a data center expo in London and Cloud World that shows live examples of that. I think it's really interesting to see an entire server immersed in liquid cooling. Very expensive, but it does work really well. There's a green project initiative for waste heat energy. A friend of mine in London actually did a startup that literally just consults on building data centers next to public pools, right? So if there's a public pool that needs to be heated, they're burning gas, they're burning natural gas, or they're burning some kind of energy to heat that pool. That's a waste, right? Data centers have the heat and they need to get rid of it. So it's very efficient to do a heat exchange with a pool where possible, or some other water cooling that needs to be warmed. Neighborhoods are being heated in Scandinavia, as far as I know. There was a concept that Microsoft ironically patented, I think, probably 15, 18 years ago now, the data furnace, right? So they would essentially build a half rack into your home, use that compute for their needs, and that waste heat would heat your home and heat your water, right? That's a concept that I wish would come back. It took off a little bit in the Netherlands, I think, a while, and then it just kind of fizzled. Carefully consider the core maximum count and speed, because guess what? Again, the more cores does not necessarily equal faster. If you've got 64 cores in your CPU, guess what? That's going to overheat way faster than you think, right? So you may advertise a speed of 3 gigahertz and 64 cores. If you exercise all of those cores at once, I guarantee you, without proper cooling, that core speed will quickly hit a fraction of what it should be, a quarter of the speed that it should be. And in fact, a lot of the latest Intel chips, including this laptop, they advertised a turbo boost of, say, 4 gigahertz, but you're only going to achieve that 4 gigahertz for a fraction of a second, right? Because core speeds are changing constantly in response to thermal needs and workloads. So always monitor your core speeds. Again, CPU performance can be clocked at 100% utilization, but that 100% utilization covers all core speeds. So even if you're going a fraction, 400 megahertz. Okay. If you need a single thread or a single process to be maximum speed, go lower core count, right? 4 CPU cores at 4 gigahertz is sometimes faster than 16 cores at 4 gigahertz, because that's the way cooling works. You're going to overheat those cores, and eventually you're going to not perform as fast as the lower core count device. Okay. Again, tuned profiles. Always use tuned profiles. I've been on several ARM servers that actually don't benefit from this. And it's funny because some of the ARM servers, and if you're using a Mac with Apple Silicon, they don't necessarily follow the same Intel recommendations as for the S states, right? The power states of the CPU. ARM generally is pretty good at optimizing its own speed. And again, obviously, if you use a MacBook and your battery lasts for 16 hours, good for you, right? The server side is now seeing that as well, performance. Utilize offload and coprocessors. Again, smart NICs, TCP offloading are features that I see coming back now. I love to see that. One thing else that we saw in the last Intel generation of MacBooks was that, again, this isn't enterprise, this isn't AI, but if you're using a laptop that has a webcam that doesn't have a hardware encoder in it, again, Intel or someone in the industry convinced users and manufacturers that the CPU is fast enough to encode video for a webcam. And in fact, this one right now, I think the webcam is webcam is on a USB bus. I think it has an encoder in it, right? That is a specialized device in your webcam for encoding video. It's cooler, it runs cooler, it's not overheating the CPU, and it's saving my CPU to actually do other things like stream, right? So run the stream, run this presentation, and so on and so forth. There's an entire generation of systems that said, oh, we'll just put all that raw video. In fact, I think Apple started this. Raw video, like if you use the Apple Iris webcam from, instead of a USB bus, from the PCI bus directly into the CPU. Now your CPU is overheating and being utilized just to do webcam video encoding, live video encoding, right? I think that was a terrible decision. Make sure your webcam supports offloaded hardware encoding. Okay? And again, here's the example of the TPU. If you're familiar with Google's TPUs, tensor processor units, these have been liquid cooled from day one. Right? They were always liquid cooled, and that's the way it should be. Grok as well. I'm assuming all of Grok's Grok was GROQ, not GROK, Elon Musk's. GROQ was a spinoff essentially started by some of the Grok, some of the TPU engineers from Google. Apologies. And these specialized devices, to my knowledge, are still the fastest inference machines in the industry. And we'll get to the NVIDIA Blackwell in a little bit as well. But these devices are specialized and they're liquid cooled. They should be. Don't fill a server with a bunch of fans and expect it to be able to keep up with the power that's in these GPUs, right? Again, the latest Blackwells, if you're familiar with the NVIDIA special units, NV 72, whatever the rack is, I forget. These servers, not just the servers, but each GPU is something like 600, 700 watts, right? That's a toaster oven. And you've got something like 72 of them in a rack. So think about that. You can't have air cooling going through this. You need liquid cooling. It's just going to melt. Okay. So AI inference and quantization. Again, I guess this popped over to the quantization step now. Again, this applies to the Llama.cpp work that I do and I advise customers on. Quantization, if you're not familiar, is essentially taking an AI model, one of the usually open source models, and where these vector databases and these weights of the model are stored often native in FP32, floating point 32, or floating point 16. That isn't necessarily the most efficient way to get a result. In fact, right, if I have hardware that supports FP16, FP32, that's great. That costs a lot of money, right, and a lot of compute time. And you find oftentimes that you can download a model that's a fraction of the size, maybe half the size, has floating point 4, FP4 level of detail. Essentially, it's like a low resolution version of the model, and it still gives a perfectly valid answer, right? In fact, I would say that lower detail often makes a model a little more human, right? Because there are mistakes involved and it surprises you. So there's a great YouTube channel, one of my favorite YouTube channels on this topic, Trellis Research. It's a guy named Ronan out of Dublin. And he highlights brilliantly how you can download a model. And in this case, again, I have a Volta workstation. I have two Volta 32 gigs in my AI workstation. These are really NVIDIA's first, I would say, dedicated and breakthrough AI cards. And they're meant to handle, I think, floating point 32 or floating point 16 math, right? So if I do download a quantized model, which I do all the time, and I'll use a floating point 4 or essentially quantized down to 4-bit model, it's faster, right? And it stores in memory smaller. It takes up a lot less memory, which is probably the main benefit to it. But then each time all those vectors get put through a GPU, they have to be upscaled. They have to be essentially cast to the register size, right? Or whatever, FP4, FP16, FP32, right? So I am essentially processing the same speed, but I'm using less memory, right? So each time I'm predicting the next token, I have to read maybe a 24 gigabyte model through the memory, and for that to happen 32 times a second, that requires a lot of memory bandwidth, right? And Voltas that I use, I think, have a terabyte per second or 900 gigs per second bandwidth, right? Your gaming GPU probably has about 200, 300 gigs a second tops, right? And I think Apple M2 or 3, I could be wrong. I think they have 128 gigs per second. No, 128-bit bus. I forget. Memory bandwidth comes out in inference. That is the biggest bottleneck in inference. Now, if you're wondering the difference between the generations of Intel, I'm sorry, of NVIDIA's GPUs, again, the Blackwell series, there's a great video, and I'll link to the Trellis research page. Essentially, the Blackwell series is flexible, right? If I can do FP32, floating point 32 math, in a 32-bit register, or obviously a 64-bit register, normally I would have to do those one at a time, right? Even if I have a floating point 4-bit number coming in that I need to crunch in an inference cycle, I'm going to have to use an entire cycle for that, right? Well, guess what? Blackwell is much better at scaling that from it. So instead of just one 64-bit and one 32-bit register doing a single FP4 calculation at a time, I'm going to cram in as many of those FP4s as I can, right? So I think it's like an 8 by 4, it's 32-bit, yeah. So 8 FP4 calculations in one cycle, right? So it scales enormously when it comes to quantized math. Blackwell is very flexible. I still don't own one, and I'll probably get maybe when I get back into the States, when I leave Malaysia, I'll probably get a consumer model like a 50X, RTX 50 something, just to test the development of it. But the NPUs, again, the neural processor cores inside the Blackwell series are really good at flexible quantization. There's hours and hours of Ronan's talks on YouTube. I highly recommend them. He explains them at as far as I can tell, a PhD level, which is beyond me. But it's really enlightening to see how this works. Right? So again, if you're going to be doing a quantized inference, if that's what you're working on, not just the system heat, but actually the generation of your hardware makes a big difference. And if you're using something like a specialist solution like the TPUs from Google, or again, a Grox LPUs, language processing units, those are going to make a huge difference as well. Now, the last bit again, bottleneck, memory and bandwidth. This is what I was talking about earlier. A lot of people, again, think a gaming GPU or their phone can do inference in the field. Yes, they can, but do you really want them to, right? So you need to consider this memory bandwidth if you're doing AI on your own, right? So again, people trying to do field devices like a Raspberry Pi 5 in the field. I have one customer, again, that was trying to run Whisper.cpp. So that's the voice recognition models from from OpenAI, being run on the Llama.cpp runtime, actually the Whisper.cpp runtime. Now, you can actually run this on your phone and WebAssembly. It's kind of fun. And I had a customer say, okay, well, we want to do this in the field with some of our devices that have a Raspberry Pi backend. Can we arrange that? And guess what? The memory bandwidth limitations of a Raspberry Pi or essentially a small SBC, like a Banana Pi, etc., that is your limiting factor, right? So the GPU may be able to handle it in a small ARM device, especially with the new things that Qualcomm are coming up with. The memory bandwidth will tend to be your limiting factor. So if anybody wants benchmark details about that, I can show some actual results in the field that we had. Again, Intel or Apple systems, your memory bandwidth goes up from a small Raspberry Pi device, which, to be fair, consumes almost no power, 10, 15 watts. Intel and Apple systems can typically go from 120 megabytes a second to 500 megabytes a second. Again, the NVIDIA cards that I use, the Volta V100s, are connected together with NVLink. Each card has a terabyte a second, right? That is the difference between a 10-year-old, 8-year-old AI GPU, which costs a lot. I think they're worth it still about $1,000 or $1,500, and an 8-year-old gaming GPU, right, which doesn't have the HBM memory. The NVIDIA Ada through Hopper Lake which are based on, I believe, HBM3. Mine are HBM2, I believe. High bandwidth 3 memory. Again, the bandwidth goes from 1 terabyte to 4 terabytes a second. That is huge. This is why the H series was all the rage from the past generation. I think the rumor has it, again, OpenAI started out with the Volta series, what I have in the ZGX1, and they had, I think, 4 or 8 in a single server connected with NVLink on SXM instead of mine are PCI, right? It's a standard that you put in your server or your workstation. They have their own fans, right? That's enough to train essentially what became GPT-3, 3.5, right? Further models, right, are using bigger guns, Ada and Hopper Lake. Again, Blackwell. Guess what? If you're just a small startup that's doing language, if you want to make a custom kind of a fine-tuned model for a chatbot for your customers that knows your products and knows your support database, do you need a Blackwell? No, not necessarily, right? I've got customers and clients that are still custom tuning their own models that work just fine on older systems. Or if you get a cloud instance of Volta 100, it's pretty darn cheap now because they're probably almost end of life. NVIDIA is going to supposedly not support them in a year or two. They're still perfectly valid for language models. Right? It doesn't take much to tune an additional database or an additional customer use case for your own purposes using yesterday's hardware. Right? Blackwell, Ada, Hopper, all these super expensive GPUs that cost, I don't know, like $20,000 to $50,000 and more. These are good for what? Pictures and video. Well, not many people are doing pictures and video, right? The standard use case for most businesses still tends to be, when it comes to training, still tends to be language. And that can be done with yesterday's hardware. Again, inference is different, right? Inference, if you're large scale inference to the size of essentially a ChatGPT, you need auto scaling. Blackwell series are even, I don't know, Blackwell series if you're lucky, right? Blackwell's very hard to get right now. Again, Grok, I'm a big fan of Grok. Guess what? They're using SRAM. You go from 1 terabyte a second, 4 terabytes a second, maybe the Blackwell series, which uses HBM3, up to 2 by 4 terabytes a second. Grok's LPUs with SRAM are looking at 80 terabytes a second. Right? That's a huge leap, and this is why one reason why Grok is so successful. Right? They are built just for inference, just on quantized inference using essentially the fastest memory that you can have. Okay, that makes a big difference. So eliminate your bottlenecks, use the fastest memory you can, and if you don't need to do pictures or video, you don't need to scale to the likes of ChatGPT and to a lesser extent Grok, then you're just fine with last year's hardware. Okay. All right, and I've probably overrun. I hope that's okay. We'll stop and ask for questions.
Yeah, it was really in-depth topics you touched upon. Yeah, I was following all the parts. It was interesting in terms of the bottlenecks. If Atakan has questions, maybe Atakan could start, or I can start my questions. How we could
Yeah,
do it.
sure.
Yeah, I have one question about so the overall during throughout the presentation, like from your experience, you almost like talked about the network latency and stuff. But have you ever seen, especially with this accelerators, now there we have this paravirtualization and shared GPUs, and was there any like a latency that you've seen in the field related to this Virtio drivers or this pass-through?
Yeah, that's funny. Good question, actually. Vert passed through, and there was NVIDIA Grid for a while, right? So they created a way to sort of divvy up cards or essentially use the concept of a control group, right? A Linux control group or namespace to say, okay, well, you get a fraction of this GPU. I've not seen that myself. In fact, it's funny because I gave a talk in London on inference, and I had a contest where I gave away an older NVIDIA GPU. It was a Maxwell. It was an M10. And it was funny because this actually wasn't an AI GPU. It was a single PCIe card that was designed for virtualization, exactly this. It had 4 GPUs on one card, right? 4 by 8 gigs, so that essentially a VM could get its own GPU in the server in the host. And it was essentially a hardware pass-through, like you said. It was designed for this. And as I understand, it worked very well. Actually, people that used it, it worked very well. In fact, the only latency again you'll have then, the system will respond like it's a perfectly usable GPU, right? But then the end user sees it on a screen from the network away. So the latency between your system and your GPU is almost zero, but the actual latency to your screen is a problem, right? So that has to be considered as well. No, NVIDIA did a really good job of essentially designing this, right? Designing GPUs to be shared, to be passed through virtually. Again, VirtIO drivers were adapted on the fly. They kept up with the NVIDIA tech really well. I have seen, again, in the early days, people actually would do a Virt pass-through and reserve an entire device. And that means that that device is no longer available for someone else. You have contention in that sense, right? So someone else wants a device, they have to wait their turn. In fact, anybody that uses NVIDIA's cloud gaming, what is it called? NVIDIA Go? It's funny that this is still an issue even for gaming, right? You have to wait for a system to be available. They don't essentially divide up GPUs for cloud streaming. So no, I think it's very well. NVIDIA knows their stuff, right? They know exactly what the customer needs and what they want. And in fact, I've seen innovation. I've seen features be released for NVIDIA, and to my own shame, wondered like, well, who's going to use that? And sure enough, within a year, there's a new feature that makes perfect sense. Why NVIDIA did this? They're thinking 2 steps ahead, right? That's what they do best.
All right. Thank you.
Sure.
Yeah, I have a couple of questions also. Thanks for the presentation, first of all. You talked about a lot of bottlenecks, about thermal storage, I don't know, network. In your opinion, like in your experience, what's the most costly bottleneck for the organizations in terms of money or resources?
Most costly bottleneck.
Like, for example, the company like first of all, like should focus on like solving that problem, prioritization.
Sure. I don't want to play the cloud card, but I see everybody going cloud first without testing their speed, right? Always benchmark. And in fact, when I was at Red Hat for a while, they inserted me into Dell public sector in the UK, and there was no objective. There's just, how do we sell Red Hat and Dell together? And I said, well, guess what? Give me your latest top of the line boxes for a week. Let me benchmark them and show that it's working. Can you see me? Can you hear me okay? I just saw that essentially my connection is gone. I said, let me benchmark those devices. Let me make sure that we have reports that show how they perform. Right? No customer should make a big investment like that without a trial. And again, I've seen customers that were overpromised by sales many times. Oftentimes, like I get sent in, like something isn't performing well. Our sales rep said it was supposed to be 100 times faster than it is. Okay, you've been overpromised, right? Let me find out if I can make it better. But there's always some middle ground. Again, the storage is the worst case. Our storage was supposed to perform faster. They said it was fast. Why is it slow? Well, because it's not being used correctly. And again, the case of the cloud sales. Oh, you can put Oracle database directly on the cloud. And one of my favorite fires to put out, everybody remembers healthcare.gov, right, in the US? And what essentially happened was one of the SIs, essentially one of the partners in that venture, was told, well, I just put a VM in the cloud with an Oracle database, and that's enough to support the entire country because it's cloud, it's fast. No benchmarking, it runs fine for me as a developer. Well, guess what? There's going to be a couple of million users in a week. Nobody thinks to actually benchmark things at the scale that the users would in time. Always test, always benchmark. That was my number one right off the plane. I'm here to visit. I'm here to sort out your problem. Let's run a benchmark. And then we have a baseline. Okay, how can we make this faster? And also, how do we scale it out? Right? I've seen a lot of people And a lot of the benchmarks actually included in Veronic's test suite that I talked about are designed for a single process. Okay, well, yeah, you can benchmark a single process and it will show you your performance is 1,000. Oh, well, let's actually try running 5 of those at once. And you find that your system performance is actually 5,000, right? Always be thinking about scaling up and scaling out and benchmarking accordingly. Right? So I think the biggest, most costly mistake that I've seen some customers make in the performance side, and I could do a whole other talk on security. I've seen security nightmares as well, but performance, people that are overpromised, people that either go all in on cloud on a long-term contract, and it turns out their cloud isn't what they need, right? I've seen so many people design, again, a very high level in the HashiCorp side with Terraform as well. Here's some Terraform code that makes it so easy to deploy this. Well, guess what? Your storage is in one region, your compute is in another region or another AZ. There's 5 milliseconds of latency here, and it needs 10 round trips each time you do an IO operation, right, an IOP. People need to consider these things at a lower level, right? I'm all for hardware, and it's, again, your best system administrator grew up a gamer because they knew exactly what milliseconds mattered, both in the networking front and also internal systems and cooling, right? Definitely. Sorry.
All right. Thanks a lot. Yeah, I think we can finish up here. Again, thanks John for his time and for the great insights about the bottlenecks and all the topics. And guys, that was it. That was the end of DevStandup session 16, and I hope you'll enjoy that. And as you know that every week we feature one IT specialist from the industry to share their experience, to their knowledge with other people. And if you would like to be our next guest speaker, please fill in the form under this description below, and our team will contact you, and we could have another session. Apart from that, have a nice day, guys, and let's meet in our next DevStandup. Bye bye.
Thanks, guys. Jeff, bye.